Hi, my name is Changhua from Group 4. In this part, our presentation, I will cover three things: how we prepare our data, my own experiment set board, unveiling the training sample size, and the overall conclusion for our project on protecting hotel booking cancellations. Let's start with the data preparation because all four of our experiments are built on one shared clean data sets. We made a few important decisions here. First, we dropped two reservations fields, reservations status and reservation status date, because both are only recorded after booking is already cancelled or completed. Keeping them would be data leakage. Second, we kept duplicate rows. The dataset has no booking ID, and removing them would distort the original 37% cancellation rate. So we preserved the original class distribution. Third, all encoding and scaling are fitted on the training set only. Again, to avoid leakage, and we use one unified stratified train development test split. After cleaning, we are left with 119,209 wrinkles, 31 attributes, and a 37% completion rate. Now to my part, experiment set 4. The question I investigate is simple but important. Does adding more training data always lead to the better model? And which of our models is the most data efficient? A quick word on the metrics. Because the data is imbalanced, the primary metric is the F1 score of the cancelled class, which balances precision and recall. I also looked at a second view of each model's overall discriminative power. Accuracy is less meaningful here, and note that we kept the original 37% distributions, which no resimply. For the setup, I took the single best model from each of the other three experiment sets, each with its own tuning and features. KNN for set 1, logistic regression on the 68 RFE select features from set 2, and the voting ensemble from set 3, and the diagram on the right shows I shuffle the training set once, then training each model on growing portions of the data, from 10% up to 100%. I did it cumulatively and at every step 1. I evaluate on the same fixed test site, plotting the F1 and the rectangle learning curves. Here are the learning curves, and the key finding is that more data doesn't help every model equally. Logistic regression, the orange line, plateaus almost immediately by around 20% of the data. As a linear model, it has the lowest ceiling. PNN, the blue line, is opposite. It's the most data hungry, still can be even at 100%. And the voting ensemble in green is the strongest at every training size, and also the most data efficient. It ranks an F1 about 0.83 using only half of the data, which already beats KNN trained on the entire data size. The Rocktai crew tells exactly the same story. This table summarizes the trend of each model. KNN keeps improving with more data, but never clearly plateaus. Logistic regression stays flat from very early on, and the voting ensemble rises and stays the best across every data size. So it's carried forward as our overall best model with a test F1 of 0.394. So to bring everything together across 4 experiment sets, KNN was the best single algorithm. Feature selection gives no real gain because our features are already informative. Ensembling does help, with voting beating every single model, and my set 4 confirmed that this voting ensemble is also the most data efficient. Our overall best model is therefore the soft voting ensemble of logistic regression decision tree and KNN, with a test F1 of 0.8394 and an accuracy of 88%. In practice, it can be deployed as a cancellation risk scoring system, letting hotels target high-risk booking with recommendation reminders, overbooking control, and deposit policies. And our experiment suggests that about 70% of the data is already enough to rank near best performance. That's all from me. Thank you.